Okay, so today we're going to talk about another class of caches. So we've already talked about direct map cache. So there are two other sort of cache systems that we're going to talk about today. The example of cache hierarchy and other type of examples in cache will be discussed on Wednesday. So we're going to conclude with the chapter 5, and perhaps we're going to leave some of the latter portion of chapter 5 outside the course. So after the caches, our material for the exam would be all covered. Next week on Monday, I'll try to analyze some and bring up some exam questions, just like what I did for midterm, so you have a better understanding of what to expect for your final. And then yeah, so I assume next Monday would be your last lecture, right? You don't have any Wednesdays. Yeah.
The exam's gonna be accumulative.
What does that mean?
Like, is it gonna be like covering the first part and like
I
before the midterm, after the midterm, or
I try to give you more questions about the latter part after midterm, but some of those are completely related to what you've already been taught in the previous chapters. In order to know how to, like, I don't know, read or decode and opcode, I mean, you need to know what was happening in chapter 2 or 3, right? In general, I'll try, because it's a final exam. It should be representative enough of the whole course, but I'll try to weigh the questions in a way that you have more from chapter 4 and 5.
yeah, but it is not really like directly referring to like the first part. It's just more. It's about the second part, but like you have to have like the background knowledge from.
Mostly. Yeah. I'll give you more information on that on Monday, next Monday.
How much of Verilog's going to be on the exam?
So yeah, I've been receiving many questions on this. I'm not going to ask you just to write 100 lines of Verilog. That's why you're attending labs, just like what you've been doing for the first 4 labs for assembly. So at most you're going to write a few lines, like 5, 4, 8, or just filling up some gaps or some diagrams you need to just complete. For instance, yours data path diagrams in chapter 4. You might just have to complete some portion of that. You're not going to get asked to just start from scratch. The exam time is limited. I'm not going to ask you, and it's unfair. Yeah.
Are there labs next week?
No, so tonight and tomorrow will be your last lab. It's lab N. For those who have missed any of the next, like the last 4 labs, like, and they've already emailed me and they have my approval, so they can sit in for a makeup lab next week. For those who have done their Verilog labs already, by tonight they're gonna be over. Okay, so next week you don't have any labs. Any other questions?
Are there any sample questions on Verilog that you will be posting?
Next week I'll provide. Yeah, and this weekend I'll give upload some sample questions on chapter 5 as well, so you have all of those chapters available. Yep.
Will all sections have the same time?
No, it would be different. Yeah. And that was basically your question. Yeah. Okay, so we've already discussed direct map cache, and we mentioned that just by having a tag, we understand how we're gonna map and find the location of the data in a cache that we are looking for, and it's a one-to-one search. So we don't have to search for any other locations in cache in order to find the data. Tonight we're gonna see 2 more sort of paradigm in cache systems, which are called SID associative, and we're gonna talk about it tonight. So for now, let's just have a recap on average access time that we talked about last week. So we provided the definition of AMAT as average memory access time, which is the hit time plus your miss time, and miss time would be considered as a coefficient of miss rate multiply miss penalty, right? When you miss, you have to pay a penalty by the coefficient of the rate of the miss. You have to multiply these two, and then you're going to add it to the hit time. So, for instance, if you have a CPU with 1 nanometer clock, so you have the and you have the heat time as 1 cycle, miss penalty of 20 cycle. Normally miss penalty is way higher than your heat time, and your instruction cache has miss rate of 5%, so average memory access time would be simply a multiplication of the rate of the miss and the number of miss penalty you have to pay for that plus your hit time, okay? And it's going to average out your miss and hits, so 1 becomes on average 2 cycles, okay? And we mentioned that when CPU performance increase, miss penalty becomes more significant, right? So we want to make sure that when we have a high performance CPU, we miss as little as few as possible, right? Because each miss will cause us a miss penalty, multiply the by having a higher miss rate, you're gonna have to pay the price to multiply that with the miss penalty. And if you have a very high performance CPU, this will cost you a lot. So that's why there are other paradigms of blocking data in cache, which we discussed today. Okay. So it is called. So these two are called fully associative or n-way set associative. So depending on the number of associativity, you're going to have n-way and a fully associative. So let's talk about the first one, full associative. So it's going to allow a given block to go in any cache entry. It's just the opposite direction of your direct map cache. In direct map cache, you had only one choice for each to go. In the fully associative, you have all, in any location of the cache, you can place that block. Okay, so it's other extreme end of cache systems. So, in order to find the given block in a fully associative cache, all of the entries, right, in a cache must be searched because you've allowed them to place it anywhere in the cache. So in order to find that, you need to search them all again. To make that search practical, normally we do it in parallel with comparators that are associated with each of the cache entries. So we have to compare some portion of the cache with some comparators and to find the entry in parallel, right? Of course, it's going to increase the hardware costs and effectively making the fully associative cache placement, I would say, practical for a small caches, not with a large cache size. Okay? So fully associative is just the extreme end of other spectrum of the direct map cache. Somewhere in the middle of these two, they have defined n-way set associative. So we can define some sets using a simple formula, and we only allow the blocks to be placing on that n entries. That's why that n comes from. So it could be 2, 4, 8, 16, or other numbers, right? So a set associative or an n-way set associative, it assigns n location in this case, right, for a block, and it consists of number of sets that we assign to be placed, and each of which consists of n blocks. So it's as if we are dividing our cache into smaller chunks, and we call them each set. And inside each set, you have the option to put the blocks. Okay, so this is direct map cache. There's only one place depending on the tag to place. This is a fully associative. You can put it anywhere, and somewhere in the middle you have n-way set associative. You divide it by the number of sets, 2, 4, 8, and then inside each set they can place in their block. Okay, so the way we can find a block number is by a simple modulo of block number, modulo of set number of set in the cache. Okay, and inside each of those entries we have to search them all, right? So instead of having comparators per entry, now we're going to have only n comparators. If you have 4 sets, we need to have 4 comparators, and inside each of those sets we need to find the specific block. Okay, let's see all of these three in one example. So you have direct mapped, set associative, and fully associative, right? And you have 8 blocks on this example. So for this figure on the left, which is a direct map, there's only one cache block, right, where the memory block was 12, and that was the only place you could have placed this. That's why it's a direct map cache. You don't need to search for that because you only know that there's only the only possibility was 12. Okay. For a set associative, okay, these are the number of sets you have from 0, 1, 2, 3. So you have 4 sets, so you can represent it with 2 number. Okay, so we call it two-way associative, okay, because it's a log of that. So now you have only 4 sets to place the cache, and inside a cache, inside each set, you're free to use any block. Okay. So the memory block of 12 must be in set what? What should I write here? 4, right? So it's going to be 0. So it's going to be placed in the set 0. Okay? Yep.
Could you just go without the one?
Yeah. So by the number of sets, right? Log of the sets, log set would be your number, like n way. So we have 4 sets, so it's going to be two-way set associative, okay? 4 sets. Now, as I mentioned here, the block number modulo number of sets is going to define which set we're gonna place the cache block. So it's 12. So mod 4 is going to be 0, right? So this value should be placed in the set number 0 of this set associative, okay? If it was 11, it would have placed where? If it was 11? Yeah, because the reminder is 3, would be 3. And so we can define multiple sets depending on the number of sets, right? 2 sets, 4 sets, 8, 16. So that's why we have n-way set associative. On the other spectrum, we have a fully associative. There are no sets here. It's just the opposite extreme of direct map. You just put it anywhere you want. But you see, you have to have multiple comparators at each entry to search for that the next time you want to have it. But in the case of a set associative with a log of 4, which is 2, you need only 2 comparators, right, to search for each of those. Because inside each of the sets, you're free to place your cache block value. All right? Does that make sense?
Fully associative.
So fully associative is like inside your cache, you don't have any sets. You can place it randomly anywhere, right? But in order to find if it's a miss or hit, you need to have all these comparators, right, to search if it's a miss or hit. While if you have a set associative with a limited number of sets, in this case it was 2, because you have 4 sets, you need to have only n comparators, right? Because each of those sets, you know, by tag, you know which set to look for. But inside a set, where exactly is the block, you need to search for that, right? So you need to have that number of comparators. Does anyone know why these 12 ended up in 4 for direct map? We discussed this last week.
12 modulo 8.
That's right. It's 4, right? The block is given by tag modulo number of blocks. Okay, so that's why you know that it's 12, so definitely it's going to be directly mapped at 4. All right.
Because there are like 4, like if it is a 4-way set, 4-way set associated, then there will be 4 comparators.
Yes. Yeah. So here, n comparators, and it's corresponding to n way. So 2-way associative, you have 2 comparators. 4-way, you have 4 comparators. But for fully, you have comparators at each entry, right?
Yes.
Any more questions? Yep.
What do you mean by expensive?
Which one? So here, if you want to implement a fully associative cache, we're going to see a high-level scheme of that. You need to have multiple comparators here. So these are expensive in hardware, and it takes space in hardware, area, and also it takes energy.
Faster?
It depends. There are trade-offs. If by faster you mean lower number of miss rates, or
By cycle, fewer cycles.
so normally fully associative, you're gonna have a lower miss rate, but the access time would be higher because you have to search everywhere.
Oh.
So this is a trade-off. We're gonna discuss it. And if you have multiple layers of cache like L1, L2, and L3, so that would play a huge role on that. So that's why normally in practice, the latest computers normally use some sort of n-way associative, depending on the architecture. All right, so as a wrap-up, the position of a memory block in each of those 3 will be determined simply in direct map is the block number modulo number of blocks, what you saw here. So 12 modulo 8 blocks is going to be 4, right? For set associative, the block number mod number of set in the cache, and then all tags of all elements must be searched within that set. Okay, inside the set. When you found that this would place in set 0, inside that set 0 you need to search. That's why you have these arrows for search here. Okay. And for fully associative, the block can go anywhere. And all tags of the block must be searched. Okay? All right. So let's have an example with a cache with 8 entries, right? We have a one-way set associative. A one-way set associative has what? It's going to be a direct map, right? Because you have one way to set that cache. So this is exactly a direct map cache. And since we have 8 blocks, if you have 8-way set associative, it effectively means a fully associative. Okay, does that make sense? Why one way is a direct map, and so here we have 8 blocks, and 8-way is a fully. You can define both ways. There was a question somewhere? So in this cache we have 8 entries, so 8 blocks, 0 to 7. If you have only one way to map it, it's a direct map. So you can call it one way set associative, but everyone will call it a direct map because you have by number of tag you can just find the specific block. Okay. On 2-way set associative, you have 4 sets, set 1 up to 3, right? So you have 4 options to place the block. And each of those have tag data, okay? Because you're still having the same size of the cache, you're distributing it differently. Yep.
Yeah, so the tag is like a reference to the data.
Sometimes yes, not all the time. Yeah.
What else is the use for the tag?
So it's sort of a reference to the data or to the place of the cache, depending on the cache type. So remember, all of these you have same size of the cache, say 512. I'm sorry. It's just the way you distribute your data. Like you want to make it a direct map, which in this case seems like longer because you have one set and then you have tag and data. In two-way, you have 4 sets, so it's sort of 4 by 4 because now you have tag data and tag data, just like what you had here, right? So set 0 had 2 tags because total you must have 8 blocks, okay? So when you divide it in 4 sets, you have multiple sets of a couple tag data. If you divide it in a four-way set associative, still you have the same amount of cache, but then you have what? Now you have 4 sets. I'm sorry, you have 2 sets now, and each of those sets have 4 times tag data. Okay. Still, this is the same size as this and this. Just the way you distribute and your system, your cache paradigm is just different. And if you distribute it to 8-way set associative, it's just a fully associative. So you have only one set, so you can just call it nothing because there's only one set. So anywhere data can go, you have tag data. So 8 times. Okay.
For 4-way, it should be like 4 sets, right? Why is 2?
So 4-way.
8 sets. So why is this?
Means like in one cell you have 4 data.
So n-way set associative, you have each set contains n entries. Okay? So when you have 4-way, you have 4 entries. Each set contains 4 entries, right?
So how to find the number of sets?
Yeah. So when you have, so by block and the way you can find set, or by set and block you can find way, either way, right? It's a simple mod. So by each of those you can find the other parameters. Okay. Everyone got the idea? That was a good question.
So, can you explain me like the difference between the uses of?
Yeah. Each of those, yeah, we have an example. It's just different architectures of cache people found useful in certain circumstances. We will have a discussion later on, but in practice, depending on the type of the architecture you were designing, sometimes and the data you're accessing, if it's a spatial locality or other type of principal locality you're targeting, or if your processor is targeting a specific application to run, you might want to choose one of these 3. But in general, in a general purpose computer, normally people use some sort of an n-way set associative. Okay. So here we have 4-way set associative. So each set, inside each set, you have 4 choices, right, to place your block. So in general, for a fixed cache size, right, which all of these 4, increasing the associativity decreases the number of sets while increasing the number of elements per set, right? So you increase the sets from here to here and from here to here, it's going to decrease. So you're going to decrease number of sets. At the same time, you are increasing the number of elements per set. Okay. And as I mentioned, on average, the advantage of increasing the degree of associativity is usually it decreases the miss rate, but it adds more hardware complexity. All right, let's have an example here. Okay, that's a, you have a 4-block cache, and so we want to compare a direct mapped, a two-way set associative, and a fully associative. Okay, so the block accesses, the sequences are 0, 8, 0, 6, and 8. Recall that in order to access the block in a direct map, we just had to have mod of this with the block number. So the first one would be this mod 4, right, which is 0. The second one was 8 mod 4, which is 2. Oh, I'm sorry. Yeah, 0. Where are we? So 0 mod 4 0 8, and of course the other one mod 4 is 2. So you have this is 0, this is 0, and this is 2. Okay. So the only one that was placed at block 2 is those that have been trying to access mem of 6. Okay. The rest 0 and 8 are in the direct are directly mapped in block 0. Okay, and all of them were like misses because before that there was nothing here. So those new are shown in blue. Okay, so that was the
Just a small question. So there are 5 block addresses, right? So when you find the mod, it should be 5 instead of 4, or
we don't know the size of the cache now. We just know the blocks. If we knew the size of this cache, we could have determined the number of lines. There was another parameter. We're going to discuss it next session. Okay. So from the size, you're going to find, depending on the architecture of the cache, you can find the number of lines of the cache and the blocks or the sets, right?
They gave it to us, right? So there are 5 block addresses, so there should be 5 blocks.
No, block address sequences. So there are like 5 different instructions. They wanted to just access some data, right? So this could have been an opcode, okay? Question?
Yeah. What's the red part mean?
So these are like updating one up to another, and all of them were missed.
Oh, just updating?
Yeah. And you have misses there, yeah.
You just go with a target.
Yeah. So in order to find a specific block in a direct map, right? In a direct map cache, the way you find the specific location to search for the data, if it was there as hit or miss, right? You just have to have a mod of the tag size. So instead of tag, you're given a block access sequence. It was a simplified version of tag. So you just have to have a mod of this with your number of blocks in cache. We had 4, so this mod 4 was 0, this one was 0 again, this one 0, and this one was 2. Okay, this is still 0. So all of these 3 would be directly mapped at 0, except this one that was mapped in 2. That's why you see only mem6 are in 2, the rest of them have been placed in 0. And all of them, I mean, since it was nothing there, right, you have them all missed. Okay. So 5 accesses. In this example, we had 5 misses. So let's see the same block access sequences. Let's see what's gonna be the output of a two-way set associative. So on top. So for two-way associative, the set, so it has 2 sets, right? We have here set 1 and set 0. So the way we find which set to place is just a simple mod again. So we had what? 0, 8, 0, 8, 0, 6, 8. Yeah. So you get mod of those, and all of them are 0. Because mod of all of those to 2 is 0. Okay? So now, but inside each of the sets, where to place, now there's the issue. If you want to overwrite something, there should be a policy how to overwrite data on that. And that's another convention that in caches normally use. Normally they use least recent one or the most recent one. So depending on the policy that we talk about, we have to find a way to override the data here, because we only know that what set to use, but inside a set it's up to the designer to choose which one to override and which one to use. Okay. So in this case, assuming that this one was there, just like the previous example, 0, 0 was there. So we had, instead of 5 misses, we have 4 misses. Because simply we have a choice of which entry, right, in a set to replace on a miss. So, and I mentioned we need a replacement policy. Normally we use least recent update. I believe it was the word. Anyhow, so that L represents for the least recently used or something. Yeah, it's either used or update. So for fully associative, now we have no sets, so we can place it anywhere. You see that by the same number of sequences, which were 0, 8, 0, 6, 8. Now we have 3 misses only, and these blues are the one after the update. Okay. So the fully associative one has 4 cache blocks, right? Which is all of them are in a single set. So that's why we don't have any notion for a set. And in this example, it has the best performance. For two-way set associative, we had 4 misses. So this was 3 miss. We had 4 miss. So looking at the block address and the cache index, here we had, when block 6 was referenced, here, when we were referencing block 6, it was replacing block 8 before. Okay? So because before that 8 was there. And since block 8 was recently used, right? That was the policy we used. So least recently used policy. We overwrite the block 8 with block 6 here. We're going to have more examples on that, so you're going to definitely understand what was the reason behind this. Okay. But overall, as your colleague asked, how much associativity is needed normally on average. So this is a result with a spec benchmark like 2000 benchmark. On average, people have found that using a 64 kilobyte of data cache and 16 word block size. So one way associative, which is what? Direct map or full? Direct map. Okay. What's happening? Fire alarm? Time to leave. So, your direct map so a direct map has higher what was I telling? I completely forgot. Yeah. So direct map has the highest miss rate, right? When you go down towards fully associative, normally on average it's going to decrease. It's not mine. No idea what that is. All right. So next on Wednesday, we're going to see how we're going to place exactly on using a cache size and the word per block. We're going to understand using different cache paradigm how we're going to place and update that table again. So in general, we have a tag, index, and block offset in an associative cache, right? The index is used to select a set, okay? But by tag, you used to choose the block by comparison with the blocks in a set. So that was your friend's question. And block offset is the address of the desired data within the block, okay? So we have, so when you have an address for a memory address, so you can fetch these three information from that address. On Wednesday, we're going to see examples on that. Okay, so this is an example of a four-way set associative, okay? So you have four sets, and for each of those, you need to have one comparator here. It's going to compare the tag, and then the validity bit, right? And it's going to check, and if it's a hit or a miss, then we're going to need a 4-to-1 multiplexer, and then it's going to fetch the data. So the cache accesses consist of indexing the appropriate set, first of all, and then searching the tags of the set, okay? And the comparators determines which element of this selected set, if any at all, right, match the tag, because they're comparing the tag, and if the validity set was set as well, of course. So you see, by increasing this, you're going to have to need more hardware and a larger multiplexer, okay? So you understand here if it was a hit or if you need to fetch some data. Okay, there are some very simple formulas on how to, depending on the set, depending on the n and the size of the cache and the length of the word, you're gonna find all of them. Okay, we have some examples on Wednesday. About the replacement policy, so yeah, that was used. So you might have multiple conventions. So the most popular one is the least recently used. Or another one could be a randomly. So you randomly update. Because in direct map, you had no choice. So there was only one choice. You don't need that. But for set associative, normally we used to have the least recently used. Okay? So in order to do that, we need to keep track of which element in a set was used recently among the others. Right? For instance, for a four-set associative, tracking when two elements were used can be normally implemented by keeping a single bit in each cache, right? Because keeping one single bit, you can decide either or not, whether or not those two elements nearby were used or not. This is just a high level. We're gonna have examples on this on Wednesday. Also, this is just for one level of cache, assuming that this was only L1. You might have multiple levels of cache. That's why we call it a memory hierarchy. You might have L2 after L1 or L3 after L2. So how are we going to define the miss rate and the average memory access time? Because, for instance, if you didn't find something in L1 and you go down to L2, you are paying a price of a miss rate and miss penalty. Then if you didn't find it here even, and you go into L3, which is larger, there is another miss here. So looking here, so you are here, right? So looking here, you are paying one miss here, one miss there, and then one miss on the third level. So you have to add them up together. So we're going to see some examples on this. All right, any questions for this? Yep.
Can you just go over the examples one more time?
Which example?
Previous. Yeah. One before. Yeah. What is the high level instruction? Yes.
High level instruction?
Yeah, are you doing a read or a write?
So yeah, we are trying to fetch some data, right? Instead of reading it from memory, right? We first look at the cache, the closest cache, which is L1. If it was there, good for us, it's a hit. If not, we have to find that data by accessing. In this case, we had only one level of cache, because after that, if it was a miss, you have to find memory of that specific location. So think about it as an opcode, right? Or an address in memory. You have to go there in memory and do a mem of that address and bring it back up to the cache, and you access it again. Okay. So here, when you look at this, you decide, for instance, for a fourth set, after the comparison for each of those sets, check with the tag and the validity set if it's a hit or not, and you have to fetch the data. Yeah.
So can you explain how much associativity slide again?
This one?
How much associativity?
Oh, this one? This is just a experimental results on multiple benchmarks on using a single cache of 64 kilobytes, right, of 16 word blocks. So this SPEC 2000 contains like 20 benchmark applications. So people run this as a standard benchmark, right? On that standard benchmarking using this cache, on average, they found that when they run using multiple cache paradigms from 1-way to 8-way, from direct map to a fully associative, on average, you're going to reduce the miss penalty, the miss rate. Okay.
But as you go down, you're also increasing access time.
Yes. Yes. Or also hardware complexity. Yeah. These are all trade-offs. So that's why normally they set somewhere in the middle, depending on their architecture.
But isn't that a 16-word block? So 8-way is fully associative for that?
Yes. So this word block is the size of the cache and the length of the addresses. So there's another parameter on that. On Wednesday, we're gonna have examples on this. How we're gonna, because we have one cache size, like 64 kilobytes, and what's the length of the word? Using that, you can find the number of blocks, and if it's a 4 set, 1 set, 2 set, right? So these are all related. They should map to each other. Okay. All right, guys. On Wednesday, we're gonna have some examples on cache, and then next Monday we have some more examples about chapter 4 and 5. Okay. Have a good night.